Okay, guys, let's get started. Second stream of the day. One day before China. I made that announcement here. Please check it out. So I won't be able to stream over the next days because of the trip, but we'll continue as soon as I'm back, and I'll be working there as well. So it's not like I'm gonna just chill and travel. So yeah. Having said that, let's get back to our tasks. We have a couple of things I want to do now. First is understand a bit better about the options we have for fuzzy deduplication. Let's see how people do that in the literature in general. The second thing I want to do is read this paper on the language identification in the wild. And then after that, let me see what makes the most sense. Yeah, I think we can transition to the filtering stage and just see, we need to understand the current LID system a bit better. What should we do and how should we train an HPS versus non-HPS system as well? We're gonna see that a bit later. I think fuzzy dedup and this will probably take the whole stream, so I won't have to plan for additional tasks. Either way, we can do that ad hoc later. Okay. So should we do first paper reading or fuzzy dedup? I think, let me see. So this is the paper that I want to check out. Just skim it from Google back in 2020 about some of the challenges for doing language identification in the wild. And I've seen weird sentences like these in my corpus as well. So I think let's start with this paper while we are still fresh. Actually, I think I feel the least fresh after I just start and after the lunch. So, but still, let's just go and read this one. Okay, language identification in the wild. Let me just paste this paper to Discord. We are reading this paper. Thanks to Chris. Okay, let's go. So, language identification in the wild, unexpected challenges on the path to 1,000 language web text corpus. That's the part that we're excited about. Understanding what's the unexpected. Moving from the unknown unknowns to the known unknowns. Something like that. Large text corpora are increasingly important for a wide variety of NLP tasks, and automatic LID is a core technology needed to collect such data sets in a multilingual context. Language ID is largely treated as solved in the literature, with models reported that achieve over 90% average F1 on as many as 1,366 languages, which is complete BS. We trained language ID models on up to 1,629 languages with comparable quality and held out, but find that human judged accuracy for web crawl text corpora created using these models is only around 5% for many lower resource languages. So we find that human judged accuracy for web crawl text corpora created using these models is only about 5%, suggesting a need for more robust evaluation. Further analysis revealed a variety of error modes arising from domain mismatch, class imbalance, language similarity, and insufficiently expressive models. We propose two classes of techniques to mitigate these errors: word list based tunable precision filters, okay, for which we release curated lists in about 500 languages, and transformer based semi-supervised lang ID models, which increase median dataset precision from 5.5 to 71.2. These techniques enable us to create an initial dataset covering 100K or more relatively clean sentences in each of the 500 plus languages, paving the way towards 1,000 language web text corpus. Okay, that's the abstract. Okay, let's quickly skim through the rest of the paper to see whether we have any charts. Model performance, representative class of noises in our initial web corpora, Manipuri, general noise, general noise, misrendered PDF, non-Unicode font. Non-Unicode font. What does that even mean? Isn't everything a part of Unicode? Boilerplate. Creative use of Unicode. My geology essay introduction, essay on man authoring cross. Unlucky frequent engram. Repeated engrams. And speak. What's and speak? They actually mention it a bit later. And speak. Lead speak. I know what's lead speak. I don't know what and speak, but I think it said it in the introduction. A surprisingly common internet phenomenon is to find text with space-separated characters. Okay. And then Kashmiri, short, ambiguous. This new model features a strong strap for a secure fit and increased comfort. High resource cousin. Uyghur, out of model cousin. Dimly. DS Suriname. Toad is deliberately obfuscated. Interesting. Okay, so there's weird things going on in these internet scale corpora, to say the least. Okay, this is just TF-IDF stuff. We're gonna see those later, some results on various languages. Future work and conclusion. Our approach yielded usable monolingual text corpora in around 600 languages. Internal user experience research suggests that web may now contain at least some amount of monolingual text in thousands of languages. So we plan to scale up with more multilingual LangID models like our language model. Truly covering the linguistic richness of the web will also need crawling approaches to be fine-tuned further. Text for some languages may only be found in PDF files, and some scripts are commonly represented in non-Unicode fonts, such as CrutiDev for Devanagari, requiring separate detection for conversion into Unicode encoded Devanagari. Applying OCR may also help handle non-Unicode text and can uncover textual content within images. And many languages that are not officially written in the Latin alphabet have informal, transliterated orthographies. Our models can identify the most common ones, but we could cover more. Finally, our work focused on the web crawl, but many new internet users primarily use their language online on social media platforms and in chat messages. Our work has looked at applying LangID to social. Our techniques should help improve LangID accuracy in this challenge domain too. What's non-Unicode font? What does non-Unicode font even mean? How can we convert it into the Unicode font? Hello, Jonas. What is non-Unicode font? Let's ask ChatGPT. Proprietary character encodings or encoding standards specific to a particular software, OS, or language. Interesting. Hi there. Welcome, neutral. Okay. And then conclusion, language ID is by no means a solved problem, that's why we're reading this. And N-gram models are much worse than popularly believed. We trained LangID models covering up to 1600 languages, but found that even seemingly high quality models were nearly unusable in practice for low resource languages. We described and analyzed several major issues encountered in applying to a real-life web crawl. Practical problems included large amount of noise, much of which appears to be natural language and can be easily filtered out. Insufficient expressiveness of N-gram models, issues with related languages, and a massive class imbalance, meaning that even 99F1 can be insufficient. To solve these issues, we developed two major improvements: tunable precision filtering methods, for which we released the word lists, and semi-supervised neural models. These allowed us to create usable monolingual text corpora using hundreds of languages based on our deep web crawl with much more and cleaner data per language than previously published approaches. Such corpora hold great promise for bringing technologies like MT and ASR to more languages, and we believe it could be possible to use the approaches we outlined to create monolingual corpora in many more languages, which should help extend language technology even further. Okay. Let's start reading. Thousands of languages are spoken in the world, but technologies like MT are available only in around 100 of them. Okay, this is like NLLB stuff. Parallel label dataset. Large sets of audio recordings and transcriptions, while MT systems have historically needed a set of bilingual sentence pairs. Parallel resources remain scarce. Language models. Okay, recently, however, significant progress has been made in cross-lingual learning models to new languages with only monolingual data. Okay, using techniques such as LabC, parallel corpora can be constructed from monolingual. It has proven challenging to derive highly multilingual text corpora from the web. One commonly cited reason is that most web content is written in widely spoken languages like English and Mandarin. Still, previous work has shown that web contains labeled and unlabeled data in thousands of languages. Since most web pages do not have any language labels attached, previous efforts to build web text corpora often rely, at least in part, on crawling selected URLs and top-level domains in each language, or use popular N-gram LIDs like fast text to target a limited number of languages. However, previous work has shown that it is possible to build highly accurate LangID systems covering 1,000+ languages. Thus, aiming to build 1,000+ language web text corpus, we trained a similar large covered LangID and used it in a large web crawl. However, we found that such LangID systems do not deliver useful results in real-world web crawl scenario. To address this, we make the following contributions. We demonstrate that LangID is much less solved than frequently believed, and popular N-gram modeling techniques have especially serious problems. We categorize common problems that these models fall prey to. We present two improvements: tunable precision word list filtering and semi-supervised transformer models, and we propose alternative evaluation metrics that better estimate the quality of LangID models. Okay, it focuses on monolingual, but the problem described also apply to parallel texts. And it is also straightforward to extend the improvements described here to parallel data crawling. Okay, previous implementations. A rich literature exists on building the text corpora from the web. We use an internal web crawler, which is equipped with robust text extraction and deduplication features and focus on expanding its lang_id component. The largest language coverage is probably Ankrubadan, which does not leverage lang_id and found small amounts of web data in about 2,000 languages. Our work is probably most similar to OSCAR and CCNet, which mine common crawl data for 166 and 174 language varieties, respectively. However, we believe depth of mining and lang_id robustness can limit the quality of datasets produced by these projects. A preliminary inspection of the often small, low-resource language corpora produced by these lang_id-based projects discovered the sort of data noise we describe in this paper, which may render them unusable for NLP. These common crawl-based datasets are also smaller than our final filter dataset, which is 20x larger than CCNet and 180 times larger than OSCAR for shared low-resource languages. One relevant lang_id implementation appearing in the above work is Dune, achieving an F1 above 0.95 for 464 languages, and offering a thorough evaluation on different data sources and domains. The only lang_id system with higher coverage than that we are aware of are those developed by Brown, with the most recent version covering as many as 1,300 languages, with accuracy about 99%. These numbers are impressive, but as we'll see, even such high accuracy on test sets will not suffice to derive useful monolingual corpora from a real-world web crawl. So now they talk about their implementation. The lang_id model we built is similar in approach to previously described systems. We use an n-gram-based CLD3 model consisting of a single hidden layer, feed-forward neural network on a bag of n-gram features and script count features, which we trained on an aggregation of proprietary and publicly available text corpora covering 1,600 language varieties with an average of 800k tokens per language. Some of the data came from sources with language tags like Wikipedia, while another subset was created using a text elicitation task where we prompted native speakers to write sentences in their language. For some languages, we also relied on the data extracted by Corpus Crawler, a tool which mines text from sites with known in-language content. Using these corpora, we trained several models on an increasingly large set of languages. As Table 1 demonstrates, even highly multilingual models achieved good F1 scores on held-out test sets. We balanced the data to have the same size, dataset size for each of the language before training. Since the relatively uncommon languages where we are targeting have little web data compared to languages like English, balancing the data makes sense in order to have a high enough recall model to get whatever scarce data there might be on the web for less common languages. Okay. Additionally, practically speaking, weighting training data according to the estimated prevalence of each language on the web at large, for example, with orders of magnitude more English example than Quechua examples, would likely make model training difficult from a computational and stability perspective. However, it is worth stressing that evaluating a model on balanced data overestimates the performance of a model on the highly imbalanced web, especially with respect to precision, as we will see in section 3.1. Okay. Just reading this again. Failure modes of LangID models on web text. Despite our LangID performing well on the held-out test set when applied on real-life web data, the models were not as accurate as we expected. This model had comparable performance to the models in Table 1, with median F1 of 96.8. At first pass filtering, we performed document consistency filtering. Okay, we ran the LangID model on every sentence in each document, and then took the most commonly predicted language as the document language. Fair enough. We only kept sentences where the sentence level and document level labels matched. Okay. All datasets were also deduplicated. This approach may have decreased recall on multilingual pages, but it reduced the severe noise problems and helped reduce disk storage needs. While we expected some accuracy loss due to domain mismatch between clean training data and noisy web text, even after document consistency filtering, the LangID labels were so noisy that the corpora for the majority of languages in our crawl were unusable for any practical NLP task. Table 2 presents some representative samples of noise. Beyond various kinds of noise, we also found a high number of unexpected misclassifications, as in the Aromo case in Table 2. The following sections detail important classes and sources of noise. Massive class imbalances. 99% accuracy is not enough. Precision, unlike recall or false positive rate, is a function of the class balance in the dataset. Measuring precision on a balanced dataset may give misleading impressions about real-world performance. For example, consider a LangID model that has 99% precision and recall and a 0.01 FPR on a particular language on a balanced development set. However, imagine, that there are 100 billion pages on the web, of which 10,000 are in the target language. In this scenario, the resulting web crawl dataset will be mostly out of language, containing just under 0.1% of sentences in the target language, insufficient for most NLP applications. Yet this assumes a relatively low FPR. For languages with a high FPR with respect to a much more, for languages with a high FPR with respect to a much more common language like Nigerian Pidgin with English, the situation is even more dire. As can be seen from this example, calculations of precision and by extension F1 are misleading when applied to real-world data with different class balances than the development set. In the general case for a classifier with recall R and false positive rate F, if we estimate that the language of interest constitutes % of the total web text, we get this number. Therefore, any evaluation of LangID should also report the false positive rate, ideally with respect to major languages on the internet like English, along with their precision and recall. This class imbalance effect exacerbates the problems described in the following sections. Okay. General internet noise and creativity. There are many kinds of web noise that are known to cause problems both with LangID and in downstream tasks, such as abbreviations, lead speak, hashtags, or non-standard Unicode encodings, like a Latin capital letter W instead of a Cyrillic capital letter WE. Just read what they say here. In the two-class case, FPR depends on the balance of the other classes with respect to each other, but not on the balance of the target class with respect to all the other classes. Percentage of English sentences classified in Nigerian Pidgin is truly balance independent. Okay. Some of these problems can be handled automatically. However, our efforts in scaling the LangID models in our web crawl to hundreds of languages uncover greater depths to internet noise alongside even more creative ways of using text. As a result of the sheer size of the web, any small pathologies of a LangID models are hugely magnified. We observe that our models tend to pick up on particular genres of internet noise for each separate language, resulting corpora for some languages that mostly showcase a rich array of particular types of oddities. For example, in our initial crawls, what purported to be the corpus for Varhadi picked up large amounts of badly encoded PDFs. Aymara and Turkmen were made mostly of misrendered non-Unicode text. Dimly had mostly invalid HTML. Dogri offered a rich array of Zalgo-like ornamentation. Fula was awash in URLs. Locano caught vast amounts of garbled JavaScript, and Zwang captured German sentences involving the Unicode soft hyphen character. In each of these cases, sadly the majority of the crawled corpus actually consisted of the class of noise that the LangID classifier decided to assign to these languages. It's almost like adversarial attack, inadvertent adversarial attack to these LIDs. Unfortunately, drawing out any in-language sentences in the corpora. In another interesting twist, one might expect that languages which are written in scripts that are not used for any other language would have clean corpora, as the unique connection between the script and the language means that any LangID model gets 100% F1 on development sets. However, this underestimates the creativity of the internet. The Cherokee syllabary, for example, contains characters that look similar to Latin, which are consequently repurposed to give words in other languages an aesthetic effect. See example in table 2, Cherokee. While other scripts such as Balinese are used commonly for purely decorative purposes alongside content in entirely unrelated languages. Balinese. Some script-unique languages like Divehi do yield high precision corpora right from the get-go, but they are the lucky few. Okay. Artifacts from character engram modeling. That was interesting piece of context around what happens on the internet. I really like this particular page. Okay, artifacts from character engram modeling. Many error modes seem to be direct consequences of engram count-based models and are also common in public corpora crawled using engram models like fasttext. Appendix E explores these phenomena in the Oscar corpus. Here are a few important classes of pathologies we discovered. See table 2 for examples of each, and Appendix C for frequency statistics. Unlikely overlap of frequent engrams with high prevalence languages. Token frequencies in natural text follow a power law distribution so that the most common engrams in a language will be present in a majority of all of its sentences. If one of these common engrams happens to occur in a sentence in a different language, LangID models can over-trigger. We observed this with Oromo, where 50% of the crawl dataset was actually English sentences containing the word essay at least 3 times, misleading the models due to high counts or the engrams ESA, ESS, blah, 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 all of which are top Oromo engrams. Ha! Interesting. That's super fun. Makes sense given how these models work. Repeated engrams. By repeating an engram sequence an arbitrary amount, which is rare in clean training text but common on the internet, the class probability of a language may be ramped up even if the language is clearly wrong. See the adversarial examples. Good fellow. This is the GAN paper, I guess. And speak. A surprisingly common internet phenomenon is to find text with space-separated characters, like this. Standard engram models or even sentence piece models can handle this without special casing. This affects about 1 to 2 languages per major script. We found that most of our Chechen data was actually Russian. Most of our Lambadi Telugu or Santali Bengali, and some of our Sepedi English. Interesting. So Russian and speak is confused as Chechen. Okay. Languages with high prevalence cousins is a specific, quite common case of the class imbalance problem, which requires somewhat different techniques to mitigate. Calling the web for a low-resource language, target language, that is closely related to a language that is highly prevalent on the internet, distractor language, can yield a dataset consisting mostly of the distractor language. A particularly salient example is Nigerian Pidgin and English, which are similar enough. The typical LangID models will have high false positive rates between the two. Because of the prevalence of English, along with its high degree of confusability, building a high precision web crawled text corpus for languages like Nigerian Pidgin is exceedingly difficult. Okay. This definitely looks like broken English. I mean, even natives would probably think this is just somebody who doesn't really speak good English speaking English. No disrespect to the language, but that's the first association here. We have this in Serbian as well. Like, I think most languages have some local communities that use it a bit differently, and then how is Nigerian? This definitely looks like English evolution. What's the thing with Nigerian Pidgin? Is this, how did this language appear? English-based Creole language. Interesting. You learn a lot. Okay, where is our... Wait, where is our... Where did I lose my... I can't find my paper, no. Give me a second, guys. I lost the paper somewhere. I'm just gonna reopen it here. Okay. Languages with out-of-model cousins. A variant on the above are languages that are not supported by the LangID model, which interfere with related languages that are supported. For example, a majority of our Uyghur role was actually Kazakh and Kyrgyz in the Arabic script. Our model has been trained to recognize Kazakh and Kyrgyz, but only in the Cyrillic alphabet. Table 2 gives an example of a Kazakh sentence that was labeled as Uyghur. Okay, again, here, because of the script, the model is confused into thinking that this is this language, but it's actually just transliterated Kyrgyz or Kazakh. Unrepresentative training data. Sometimes training data may be too clean to be accurate on out-of-domain noisy web data, yet other times it may be too noisy, too homogeneous, or contain systematic biases. For example, for some languages, training data, especially data sourced from Wikipedia, has high quantities of special characters and templated data. Template data may be harmful for n-gram models by skewing the token distribution away from that of normal text, though there is some evidence that neural models may be less affected by token distributions than by latent structure. Other training data may also have issues. For instance, in our elicited check-in data, the Cyrillic letter Palochka, not found on many keyboards, was represented with the ASCII digit 1. Our model therefore may not handle check-in text containing the correct code point or other substitutes very well. Interesting. Improving the LangID precision. Monolingual web text corpora affected by the issues described in section 3 will likely prove unusable for practical purposes. We report in 2 distinct approaches we found helpful in improving precision. Tunable precision filtering with curated word lists. We experimented with token-based filtering techniques, which are simple to implement and fast to perform on large corpora, since the LangID models in our crawl operated on character n-grams. Token-based approaches may have complementary behavior and can sidestep particular failure modes. For instance, since a sentence with the word essay likely contains mostly non-Oromo words, the havoc caused by the n-gram ESA described in section 3.3 is neatly sidestepped by checking against a curated list of known Oromo words. Such filtering approaches have the added benefit of tunable precision, allowing us to adjust the cleanliness of our corpora depending on the noise tolerance of downstream tasks. Got it. So basically, if you find such ambiguity, then just, okay, you have this n-gram ESSA, and because of the domain knowledge, you can just check, is that actual word a part of the vocabulary of the Oromo or not? Additionally, before deciding, it's like augmenting with heuristics. But this is just like very, very old way of doing things. Okay, percent threshold filtering. The simplest approach to token-based filtering is to remove any sentence where less than X% of its tokens appear in a clean list of known words for the language, such as one would find in a standard dictionary. We used in-house lists with a median of 15,000 words per language, which were obtained through frequency sorting followed by human curation. The one parameter for filtering, the percentage of in-vocabulary words, provides a simple, interpretable way to fine-tune or to tune for precision recall. We call this method percent threshold wordless filtering. Okay. Percent threshold wordless filtering. So how many percentage has to be in the vocab If it's lower than that, we filter it out. Okay, TF-IDF based filtering, but that requires the in-house lists from Google, which we don't have. There are probably some dictionaries we could use, especially for, yeah. Okay, TF-IDF based filtering. Percent threshold word list filtering is effective for a majority of the problems we saw, where the text is nonsense or in an entirely different language, but will not help where the mislabeled text is in similar language, as in Nigerian Pidgin, which has very high lexical overlap with English, meaning that such filtering will still retain most English sentences and fail to increase precision. This problem will occur with any language that has high lexical overlap with a major language. Where there is extensive borrowing of loanwords, the languages may even be unrelated, as for Chuvash and Russian. Interesting. What's this one? Interesting. Some words, however, are highly effective language markers. For example, wetin is common in Nigerian Pidgin but does not occur in English. We therefore propose to keep any sentence that has at least one word from a small list of common tokens that are distinctive to that particular language and are not shared with its more prevalent cousins. We call this disjunctive word list filtering. Okay, just a ton of different heuristics, which makes sense. First, we perform TF-IDF, where each document in our lang is our lang ID training set. However, this suffers one crucial flaw. The IDF formulation of TF-IDF weights each document equally, so a word will be equally penalized if it occurs in English or in Quiche. For practical purposes, we care mainly about filtering out common distractor language text on the internet, so we only want to penalize those languages. This motivates a simple variant on TFDF, which we call TFIF, or term frequency inverse internet frequency. This measure is the ratio of the frequency of a token in our per language corpus with the frequency of that token across the entire internet, which we approximate from a sample of 7 million randomly selected web sentences. In practice, we find that performance improves slightly when accounting for IDF and IF, yielding the TF-IDF-IF score, formally for a token T in a language L with the frequency function F term for the corpus and language-specific corpora. They get this equation with frequencies and then log 1 over sum and then 1 over the frequency. With a ranked TF-IDF-IF list for each language, we then pick the top n words for each language such that we have at least R percent recall in our depth tests. While this is tempting to choose the same R for all languages, different languages can behave quite differently with such filters, with small changes in recall sometimes leading to large changes in precision. We had best results by choosing R to be in that range and then determining the ideal precision recall trade-off on a per language basis. With this paper, we publicly released TF-IDF word list we used, covering the top 100 tokens for each of about 500 languages. Okay, that's cool. Let's see that. Word lists are omitted for higher resource languages. Okay. We don't include word lists for languages that don't use spaces, like Myanmar. Burmese. Okay. Let's see which languages they support. Do they have like Serbian? They don't. Croatian? They don't. Bosnian? They don't. Okay, they don't have any of the languages that we care about. Now, why not Croatian? Aha, there is Croatian. HR. There's Bosnian as well, but there is no Serbian. Interesting. Okay. Semi-supervised lang ID. So, okay. A separate approach from filtering is to improve our original model. Utilizing large unsupervised text corpora to improve the quality of neural networks has become increasingly important in NLP. Following this line of work, we used the noisy data crawled with our Ngram LangID model to improve the quality of our LangID system by leveraging self-supervised approaches, yielding a semi-supervised LangID system. Specifically, following the text-to-text self-supervised approach, we train a transformer big model by sampling equally from the crawl data from 212 languages. We co-train this self-supervised task with the language ID task in the text-to-text setting. With the hope of improving the quality of LangID on noisy open domain web text to reduce the confounding effect of using a higher capacity transformer, we train a baseline transformer on just the LangID task. We evaluate these SSLID models and compare against the Ngram-based LangID in table 3. In addition to F1 precision recall, we report false positive rate, whose importance was discussed there in section 3.1. All values are macro averaged over the shared 212 languages. To distinguish between apparently well-performing models, we also report the relative error reduction with respect to the Ngram, which for an error metric we define as the delta baseline model error, decimal error. We see that the transformer LangID model outperforms the Ngram model by a large margin, especially on precision and FPR. The SSLID models improve further upon this model, notably with a 40% reduction It is worth noting that these improvements are on the clean eval, despite the additional training objective being on noisy. Okay. Wait. Okay. What did they do with these models? Pulling the text to text. So I think this is the T5 paper. We train a transformer big model by sampling equally from the crawl data. We co-train, so they do language modeling plus LangID. Okay. Evaluating LangID filtering methods on web text. Okay, we're almost done here. We're almost done. Ideally, LangID models would be evaluated on a large noisy test set representative of real-life web data. Since such sets do not currently exist, we recommend having human annotators evaluate crawled corpora to ensure quality meets the threshold for downstream use, which will vary per application. For automatics metrics, we suggest focusing on false positive rate and recall rather than precision and recall, and comparing models using relative error reduction to amplify differences between apparently highly performant models, as we did above in the section 4.2. We asked human annotators to evaluate LangID quality for our web crawl text in a subset of the languages. First, we filtered the web crawl with several methods. We then randomly sampled 100 to 1,000 sentences from each of these filtered datasets and asked annotators who were fluent speakers or who spoke a closely related language to indicate whether each sentence was in the target language. Table 4 presents results. For each language, we showed the precision of the method from the human annotations and the recall of the same filter on our clean dev sets. For the percent threshold filtering, we validated a threshold of 20%, and for the disjunctive wordless filtering, we used the top N words per language such that the recall on our held out eval set was at least 90. We see that the initial datasets were extremely noisy, with a median value of 5% of sentences being in language. The filtering method drastically increased the percentage, with values of up to 99% in language, while maintaining high recall. However, the best filtering methods varies widely by language. The neural SSD has the highest precision for Bhojpuri and Swiss German, both of which also suffer most from the high prevalence cousin issue among these languages. However, it does much more poorly than wordless-based approaches on Oromo and Cherokee. In the latter case, we found that SSLID was unable to discard English sentences written in Cherokee syllabics. It is worth re-emphasizing that the threshold in Table 4 were chosen somewhat arbitrarily for the purpose of illustration. Since precision is tunable in the word-based approaches, precision can be increased further, though at growing cost of recall. A trade-off to make depending on downstream noise tolerance. Okay, Swiss German in the same situation barely scraped by. Future work should investigate additional techniques for such cases, although the most effective solution may be as simple as using a hand-curated TF-IDF-IIF list, which looked promising in preliminary experiments in Nigerian Pidgin. Using the above methods, we performed a deep crawl of the web, touching over 100 billion pages. With a 600 language LangID model, using % threshold filtering, we made a recall focused dataset, then post-filter with SSLID for high precision, yielding a larger, cleaner set and is found in similar corpora. More details and comparisons to public corpora are in the appendices E and D. Okay, we read all this. Okay. Statistics on languages most affected by different types of noise. Many of the types of noise mentioned are hard to quantify without significant extra work. For instance, it will require building special classifiers for misrendered PDFs, non-Unicode fonts, creative use of Unicode, and so on, and it may need a stronger classifier than an n-gram classifier, since after all these are mistakes of an n-gram classifier. Issues like out-of-model cousins are even trickier, probably requiring human readings. However, some types of noise can be quantified using approximations like the following. Okay. Interesting. It's going to be a ton of issues for different languages. As described in section 6, the dataset we mined has two versions, one focused on recall and one focusing on precision. Okay, comparison with Oscar, notes on curated word lists. Let's skim through this. While the analysis in the main paper focused on evaluating the quality of the data we crawled, publicly available datasets have similar issues. This section briefly analyzes the Oscar corpus, which, although an excellent resource for many languages, has lower quality content for some languages. Please note that it is hard to compare Oscar directly with our dataset. One notable confound is that the two datasets are drawing from different portions of the web. Applying the heuristic analysis from section 4, we see that repeated n-gram and n-speak issues are also very common in Oscar. Table 8 reports the 3 most affected languages per phenomena, and figure 1 shows a representative sample of 2 of these. 100% of the crawl is N speak. Interesting. Somali mostly Ngrams. Cantonese as well. Table 9. Summarize these findings along with the percentage of the corpus remaining after percent threshold filtering with our word lists. We only look at the 30 lowest resource languages in the corpus. Okay, table 9. The 30 lowest resource languages. Their human judged percent in language precision, the percentage remaining after applying the thresholding, total number of sentences in the deduplicated corpus. For languages with little or no training sentence level data, even an n-gram lang ID is not practical to train. Word-based lang ID, which assigns lang ID label to the sentence by simply counting how many known words appear in the sentence for each possible language and predicting the language with the highest count, with extra weight granted to unique words that appear only in a single language's word list. You have with what here? These are the most common n-grams, and this is for Oromo. Interesting. In table 13, we'll look at the correlation of the precision of unfiltered data in the 3 proposed filtering methods and how they correlate with 1, the size of the crawl data, the dialectical relatedness to common languages online. We hypothesize that variable 1 is a combination of variable 2 with non-linguistic noise artifacts. Okay. Or are there some macro language codes in the dataset that cover a superset of other already covered languages like Norwegian? Okay. Here's a mention of the transformer. This was my assumption. If it is computationally feasible to apply a more complex model at inference time, a transformer-based LangID system, especially code trained with a self-supervised objective on in-domain text, will have better performance, even if the held out scores seem only slightly better. Okay. Okay. Well, this paper has a ton of different heuristics, lists, and stuff. Interesting analysis. High prevalence cousin, Nigerian pidgin, and English. Okay, guys. Let's put this paper here. Go back to the to-do. Fuzzy dedup. Let's see what we can do here. Let's see what people are. Fuzzy deduplication in Python. Fuzzy deduplication for corpora. If you have any Any reading recommendations for fuzzy dedup? Let me know. Okay, let's see what we can find. This is from the Falcon paper. I think I've read this one. Let's see what else we can find here. Oh, Nordic pile. Nice. I did. This is for the Swedish. I just recently saw this Swedish large language model, and that they're using that to train. They're using Nordic pile to train their models. Let's just see what's out there. We're just gonna skim through everything. Hello. Going well. I'm just skimming a bit various fuzzy deduplication methods, trying to learn a bit more on this topic. Fuzzy duplicated look the same. Fuzzy wuzzy. Partial ratio between this is bigger than 90. When it comes to papers that first place I look for is GitHub. Yeah. We have some GitHub profiles open. The matching function entirely depends on your application. There is no silver bullet that will work for each and every case. Could not find any straightforward way to identify duplicates using Python's data science stack. Dedup. That's this one. Okay. Name. All of these are pretty much the same. Okay, so he just built some heuristics here, and then he plugged that into this algorithm of his using pandas. Let's give some of these. How these are done. Fuzzy. That's how we do it as well. Okay, LID. And then there is a fuzzy dedup here. Let me see what they say about language IDs. Language identification using fast text. So what do these guys use? They do mention fast text. Okay. So fuzzy. We found it here. Let's see. With the many subsets included in the Nordic file, some overlaps emerge, especially within the common crawl-based corpora. However, documents may be considered duplicates while not being identical. Consider an example where only a few characters of word differ, or where only a subset of the document is duplicated. These are not trivial to identify, and decisions have to be made about how similar documents must be to be considered duplicates. There are two major algorithms used for this in the literature. Okay, evaluated and compared by Lee. Nice. You can check out the paper. These are extract substring matching using suffix arrays and min hash LSH. I've seen this one used quite often. For explanations of how these methods work and are implemented along with selected parameters, see Appendix A. Okay, we can check out the Appendix A section. We opted for the min hash, and its purpose is to identify groups of duplicated documents from which only one is kept. Despite it being an efficient algorithm, the duplication of massive datasets is inevitably computationally expensive. During this work, we had access to machines with at most 256 gigabytes of RAM. With our limited resources, it is difficult to duplicate the entire dataset as one. Furthermore, experiments show that our implementation required roughly 3 times the dataset size for deduplication. To avoid crashes, we added some margins and never deduplicated subsets of more than 80 gigabytes at a time. Okay, therefore we relied on sharding the data and deduplicating shards separately, intra-shard, or pairwise, inter-shard. The first form of sharding is a product Just a second, guys. The first form of sharding is a product of the previous language segmentation step, and we do not deduplicate across anything cross-language. This should not have major impact on the result, assuming that fuzzy duplicate documents are rarely identified with different languages. For all languages except Icelandic, the datasets were of sizes greater than 80 gigabytes, forcing us to further segment the data into smaller shards. We decided that our Nordic language datasets were more prone to include many duplicate documents. Since we included several data sources, we decided that our Nordic language datasets were more prone, since we included several data sources from Common Crawl that may overlap for these languages. So our English data was deduplicated intra-shard, and the Nordic data except Icelandic was deduplicated inter-shard. Let me just see whether I got this right. Pairwise. Well, didn't they just say that they are not deduplicating across different languages, and now they say they are? Or am I misunderstanding something? So the first form of sharding is a product of the previous language segmentation, and we do not deduplicate anything cross-language. Okay, so every language was bigger than 80 gigabytes except for Icelandic, so they had to further shard. We decided that our Nordic language datasets were more prone to include many duplicate documents, since we included several data sources from Common Crawl. Okay. Intra-shard. Intra-shard deduplication divides the data of one language into shards, each maximally 80 gigabytes. Then each shard is deduplicated separately, and duplicates across shards will not be identified. This type of shard is hence suboptimal for finding duplicates, but requires significantly less resources. Well, then later you can just change the way you're sharding and do it again, and then in expectation it's going to be better and better. Okay, so since the English data was already to a large extent deduplicated with less overlapping subsets, we deemed this method sufficient. When sharding the English data, we aimed for having each shard include as similar data as possible. Inter-shard deduplication is proxy for complete deduplication and theoretically achieves the same results as deduplicating everything together. We divide the data of a language into shards of at maximum 40 gigabytes. This accounts for half the previous memory constraint to enable pairwise deduplication. Using this approach, we sacrifice computational performance to reduce the memory constraint of complete deduplication. After dividing the data into n shards of accepted size, there are two steps to this approach. So pairwise deduplication deduplicates all shard pairs separately, each pair as one concatenated data set. This setup is equivalent to a complete graph with n nodes and e edges, each node and edge corresponding to a shard and a pairwise deduplication respectively. The number of edges of a complete graph is shown in equation 1. The computational sacrifice of this method is now evident. Each shard is part of n-1 pairs and therefore redundantly duplicated many times. While the stochastic nature of min cache may entail that more than one deduplication of a single shard is beneficial, it is hardly compute efficient. Nevertheless, this step outputs a set of groups containing duplicated documents for each shard pair, which are combined in the next step. Merging of duplicate groups. Combines the duplicate groups by identifying connected components. The naive approach would keep one document from each of the found groups, but would allow for significantly more duplicate documents to slip through. Since we have deduplicated all shard pairs, each duplicate group may only contain documents from at most 2 shards, while a complete deduplication could find groups with documents from all shards. By merging groups from all shard pairs, we can approximate the behavior of a full deduplication. For instance, consider any group GI and GJK, including documents from shards IJK. With at least one common document in these groups, we can consider them part of the same group and hence merge them. I don't think we'll have to do this for now. Additionally, whenever 2 groups share a document, we merge these nodes and thus create a connection between the groups. Whenever 2 groups share a document, this reduces the problem to identification of connected components where only one document is kept from each component. We have, through this process, evaded the memory constraints and achieved thorough fuzzy deduplication of our data in the Nordic languages. Appendix B provides an overview of the selected sharding method for each language. Cool. This stage is theoretically trivial and was merely a technical hurdle given the data size and the large number of files. At this point in the pipeline, the data is segmented into 2 levels, language and shards. Here we merge all non-removed documents to the original unified dataset, dividing only into the original categories. Now the dataset is in its final format with only documents deemed clean and unique, along with additional document level metadata. While the absolute majority of the data was processed in the pipeline described, some deviations emerged for practical reasons. Examples of this are more data coming in after the duplication step and additional filtering required after encountering errors or undesired behavior during tokenization or model training. Cool. We are using Opus ourselves. It's interesting how big of an impact Pile had as a dataset from Illuthor AI. Python, JavaScript, some percentage, books. Data removed. Language distribution of the final data set. Let's see what these work, how these work. I'm also curious about the quality filters they've used. Let me just quickly check that. Quality, deduplication, language segmentation, exact, normalization, metrics, quality filtering, exact, LID, fuzzy, and merging. All of these are done on the document level and are thus embarrassingly parallel. Publicly available on GitHub for the first 3 steps. And the 4 last steps, which is weird way to say everything is supported. Okay, but on different places. Okay. This step ensures that documents are consistently encoded and perform the following operations. Non-printing character removal removes unwanted characters that may be hidden in the document, for instance, control characters such as soft hyphens or non-breaking spaces. What's a soft hyphen? Soft hyphen, non-breaking space. Huh. Okay. White space normalization converts uniform white space to center white space. Unicode normalization. NFC Unicode normalization. Motivation to opt for NFC is its non-destructive transformation. After normalizing the text, document level metrics are added as metadata. Language, number of characters, number of UTF-8 bytes, number of words, sentences, and MD5 hash. Interesting. Quality filtering. DeepMind's Gopher paper. Whenever a document does not meet the filter criterion, we save that information in document's metadata to facilitate later data. Just a second, guys. I'll be back in a couple of minutes. Okay, guys. Let's go back. All of a sudden, I have 13 people. What happened? Why do I leave for a second and all of a sudden I have a ton of people here? Okay. Wrapping up the paper on... We're just trying to find the fuzzy deduplication implementations across the literature. It seems it's mostly using... People are mostly using min hash. So again, this Nordic pile paper was inspired mostly by Gopher from DeepMind. And let me see, we have not used all filters for all data categories. Whenever a document does not meet the filter criterion, we save that information in the document's metadata. Blah, blah, blah. When a document is removed, it is not present in the succeeding pipeline stages. Below follows description for each of the 16 filters used. If the statement above the document is false, the document is removed. At least 80% of the words contain an alphabetic character. Okay. Blacklist URLs. The URL is not malformed, and the domain, file extension, and URL are not blacklisted. If a URL is not available, this filter is skipped. Okay. Digit fraction, the digit character ratio is less than 0.2%. Number of characters is greater than 50. The ellipsis to word ratio is less than 0.1. Flag words. Each flag word is coupled with a weight in the range 0 to 1, where higher weights are worse. The document contains less than 4 total flag words and less than 3 unique flag words. And the sum of weights is less than blah blah blah. Hashtag to word ratio. Initial bullet points, less than 90% of the lines start with the bullet point, or such lines occur less than 3 times. Okay, mean line length. The mean of the median value and mean value. The mean number of characters per non-empty line is greater than 9. Okay, a ton of heuristics that are not going to be useful for us as much. Mean word length. Repetitive BSP. The document is not considered repetitive according to the filter for repetition used for roots. Details for this filter were found in their source code and is complementary to repetitive Gopher filter based on characters and words. The document is not considered repetitive according to the repetition removal filter described in Gopher based on n-grams, lines, and paragraphs. Our implementation differs in that it is word-based, whereas the original implementation is token-based. To account for this, in our multilingual data, the thresholds are adjusted and are shown in table 1. Stop word contains at least 2 words. Danish, English, Icelandic, Norwegian, or Swedish. Dwelling ellipsis, less than 30% of the lines, and with an ellipsis or such lines occur less than 3 times. Okay. Okay, so those are some quality duplication, quality filters they are using, and then it goes dedup and the fuzzy. Let's go to the appendix section quickly. Sharding, quality filter configuration. Let's see some of these examples they filter out. The number of documents that are considered duplicates of each other within the group. For each example document, a snippet of the first 200 characters shown. Line breaks have been omitted. Okay, I don't really speak the language, so it doesn't really matter for me. So each data source is mapped to its own configuration if present, otherwise to its categories configuration, with the following exceptions, modifications. Opus uses the webcc configuration. What's webcc? Okay, let's read this on the deduplication. Exact substring matching identifies duplicate substrings across documents and removes them from the documents. A naive approach would be quadratic with respect to the number of documents, and the solution used by these guys uses suffix arrays. All documents are concatenated to one massive sequence for which the suffix array is created in linear time. This data structure enables identification of duplicate substrings with linear complexity. This can also be done over tokenized data, which may reduce the compute required. Finds and removes all duplicate substrings longer than 50 BPE tokens. And then comes a second method that this paper used. Min-hash LSH identifies approximate duplicates on the document level and is widely used in the literature. Brown, this is I guess GPT-3 paper. Gao, this is Chinchilla, I think. All of the LM papers basically. The core idea of this method is to represent a pair of documents as CI and CJ as sets SI and SJ, which can be done in many ways, and measure their similarity using the Jacquard similarity. We use this approach for fuzzy dedup as it is commonly seen in the literature and has available implementations which we could easily adapt and use. Number 8. I'm gonna check it out. Fuzz. Okay, so if the union, the size of this set over the size of the union, intersection over the size of the union, a naive approach would measure the similarity of each document pair and would result in a quadratic scaling for the hundreds of millions of documents. This algorithm addresses this and includes 3 primary steps. Shingling converts documents to integer sets through character-based n-grams. We use 10 grams. This also caches each shingle to a 32-bit integer, simply to be able to work with integers in the next step and should not be confused with the cache functions used there. Shingling. This is probably the first time I hear that word. Shingling. Okay. Min-hashing converts each large integer set to a small sequence of p integers that preserve similarity. While this explanation does not provide strong intuition for why the algorithm works, The concrete steps to create these fingerprints are the following. Create p-hash functions, each acting as a permutation operation of the integer set shingles. Define the function as the minimum value of the permuted hash shingles sequence for each pi h sub pi of c converts the shingle sequence to a single integer, resulting in a sequence of p integers for each document, often referred to as fingerprints. We use p10 hash functions to achieve balance between computational cost and the deduplication accuracy. Locality sensitive hashing. Find signature pairs are likely created from similar documents, while min hashing can significantly reduce the computational effort required to find the duplicates. By comparing the fingerprints instead of shingles or even whole documents, it still suffers from quadratic complexity with respect to the number of documents. This step removes the need for comparing all document pairs through hash collisions. First, the fingerprints are sliced into B smaller bands. Each band is then independently managed in its corresponding bin, where it can be compared with other documents band in the same position. A hash map is created for each bin, mapping a hashed fingerprint. Lastly, all candidates found are iterated, and for each candidate pair, the Jacquard similarity is computed. If the similarity exceeds the threshold, the documents are considered duplicates. We use the threshold of 0.5. Now duplicate documents are connected and duplicate groups can be formed. For each group, we remove all but one document. Okay, that's hard to understand from just this paper, but we now know what they've used, and that's min hash. Okay. I think we found this one already before. Shingle min hash LSH. Data sketching is a method to summarize or extract meaningful metrics from a dataset with which to compare with other datasets, and min hash or shingle min hash is one method. Sim cache. Okay, interesting. Let's go back here. Yeah, we can close down this paper. I think we found the answer. Basically, there is now going to be a ton of different projects that do this. So this is the explanation of the whole thing. Sim. This looks good as well. Fuzzy. Cache. We can check this as well. I'm gonna quickly skim through this, but yeah, it's gonna be always the same algorithm basically. Okay. It's Blink. We don't care about none of these. I'm just selecting, reducing the number of things we're gonna skim. We don't care about this one as well. So let's see how these two papers used it. These three repos, and this is a bit more in-depth explanation. So quickly skim through the papers later, skim through this blog, read through this a bit as well, and then see how people are using it here. Okay, guys, I think with that, I'm wrapping up this stream, off to a break, and then after the stream, we're gonna continue with the fuzzy dedup, just exploring a bit how the whole process of shingling to minhash to LSH works, and how we can basically implement this in our own code base. That's it. Catch you after the break, guys. I see somebody shingling sounds more complex than the process. Yeah, it's just a word, nothing special there. I mean, you can probably figure out what's going on. I could probably understand exactly how it works in a couple of days, but I'm not sure whether we need to do that. Okay, cheers. See you after, let's say 8:45 p.m. So that's in roughly 1 hour and 45 minutes. Until then, bye guys. See you later.